We'll see how well you can hear me. I've been unmuted the whole time, so you've heard me shuffling around. All right, so yeah, morning was a mess. I came to the lab when I shouldn't have. All right, I'm gonna try to do this on the virtual lab. Okay, so the lab today is about Zener diodes. So the lab's posted on Canvas. You should be able to see it. We've talked about Zener diodes in lecture already, so we're going to do some simple measurements, forward bias and reverse bias. So this circuit right here, wait, hold on, I got to share the screen, don't I? And it won't let me minimize. There we go. More stuff to put on the screen. Okay. Yeah, so we're just doing a simple measurement on Zener diodes in forward bias and reverse bias. So this would be a reverse bias Zener diode circuit, 10 volt supply, 470 ohm resistor. 4733A is a 5.1 volt, I believe. 5.6 or 5.1, I can't remember. We'll double check that in a moment. But remember how different Zener diode part numbers have different turn-on voltages, right? The Zener voltage, VZ. And so there's some background information on how to calculate the current or voltage drop in forward bias and reverse bias. So in this one, I didn't flip the diode, I flipped the supply instead. Notice that the power supply is pointing down now instead of pointing up. So that would put the Zener diode into the forward bias region. So we expect it to drop 0.7 volts in that region. Okay, then we can explore that simple power supply circuit also that we discussed in lecture. So that one, we're going to look at where exactly does the Zener diode turn off and where does it turn on. So remember how we calculated the exact level of resistance that would be necessary to turn it on or turn it off. So I think when we get down to the actual lab part, so yeah, for that one, we're going to adjust RL. So we're going to have different values of RL, and then we're going to measure and calculate all these quantities and compare them. Okay, let me try to pull up that virtual lab and see if I can show you some of these measurements. Okay, hopefully you can still see that in Zoom. That looks okay. That's weird. Okay, so I'm just going to go to place component and start looking for the components we need for this. So we have the diodes category here, and inside of the diodes category, you have lots of different subcategories. So you have a regular diode, you have a Zener diode, you have switching diodes, LEDs, photodiodes. This is a bridge rectifier, full wave bridge. We'll talk about that later in the course. And then a few other types. Let me go to the Zener diode category here. And for the lab, get Zoom out of the way. Okay, so for the lab, we're using a 4739 Zener diode. Okay, let me get back to grabbing that. This is hard to maneuver. Okay, so I'm looking for a 4739. Okay, so it's this one right here. So for the 4739, just grab it, drop it into your schematic, and then some resistors. So the first circuit is a 1.5K resistor. So go to basic, go to resistor. Okay, so now I got the resistor. Now I need a power supply. Go to sources and then DC power. And then I'm also going to need a ground symbol. I'm not sure why scrolling always scrolls to the end of the list every time I do anything. All right, so it was a 15 volt source and a 1.5K resistor. Okay, let me use a multimeter to measure the voltage of that diode. And then I use another meter to measure the current. You can do flip horizontal to make the right terminal the plus and the left terminal the minus. Oops. So I'm going to insert it in series. So that meter is measuring the total current in the circuit. This other meter is measuring the voltage across the diode. Okay, and I'm going to run it. It doesn't seem right. Oh, it's because one of the meters is set to voltage instead of current. It's a 9.1 volt Zener diode, so I should get 9.1 there. All right, that's better. I guess what was happening was since this other meter was set to voltage, it was acting like a large resistance in series. Still not sure why exactly 7.5, but okay, so that looks better. We're getting 9.05 across the diode, and I'm getting a current of about 3.967. Okay, so that's how I can measure the diode in reverse bias. If I want to measure it in forward bias, I can flip my source around. You can also cheat and just kind of put in a negative number here. If you just put in -15 there, that's the same thing as flipping your source around. Then you don't have to actually rewire anything. So if I do that, I would expect there to be about a 0.7 volt drop or something like we would see in a silicon diode. So I'm seeing a voltage of -552 millivolts. So that's about -0.552 volts. So again, it's sort of somewhat close to the 0.6, 0.7 that we're familiar with a silicon diode when we have it in forward bias. Okay, so you can get the measurements for forward and reverse bias by just doing something like that. And we see that it drops something close to a regular diode, a regular conventional silicon diode, when it's forward biased, which is what it is right now, right? Because the source is negative, which means the positive is actually on the bottom, and it's trying to push current down. So you'd expect a negative reading on the ammeter because current is flowing into the negative terminal of the ammeter first and out of the positive. So that's why we're getting a negative reading on the ammeter. And then we're also getting a negative reading on the voltmeter because the voltage drop is positive on the bottom and minus on the top. And the value is somewhat close to a standard conventional diode. So just by flipping the polarity, the diode actually conducts in both different polarities. And we can see that through this simulation. So going back to positive, it should drop about 9.1 volts. So that 9.1 volts is at a certain level of current. So we're a little bit below that level of current most likely. And that's why our voltage is coming out a little bit lower. Just like when we have a conventional diode that's supposed to drop 0.7 volts and it ends up dropping 0.6 or 0.65. It's the same idea. Okay, so you can do that with the forward bias and reverse bias to get those measurements. And the last part of the lab is to so just to reiterate, the first part here is just measure it in forward bias and reverse bias, record the current and voltage for each of those. So that's what I just did there. You can calculate those from theory and then compare. Okay, the next circuit is something like what we were discussing with that simple power supply. Okay, so what I have here is I have a voltage source, I have a resistor in series, and then I have a load resistor, which I'm going to use a potentiometer or a variable resistor as, and then I have that same 1N4739 Zener diode. Okay, so we said at different levels of resistance and at different power supply voltages, this Zener diode will be on or off. And it's on or off depending on the ratio of these resistors and the power supply, which sets a particular voltage across it. So if you try to set a voltage that's larger than VZ, then the diode will turn on. Right? We talked about how we use voltage divider to calculate the initial voltage, to calculate if the diode should be on or not. If it's on, then in this case, the Zener diode will drop exactly 9.1 volts. If it's off, then the voltage will be set by whatever the voltage divider equation gives you. And we also showed exactly what level of resistance would cause it to be on or off. So let's just reiterate that calculation real quick. Everything is laggy. Actually, I think it's in the handout. Let me just go to that because it seems to be writing right now is not cooperating. Put too much stress on my laptop. Okay, yeah, it's right here in the lab handout. So this is the voltage divider equation, and what we want is the voltage. So this is actually saying that when the diode turns off. Yeah. So this is if this is true here, if this left side of the inequality is less than VZ, then that means the diode will be off and the voltage across the diode will be whatever you get from this voltage divider calculation. If you do this voltage divider calculation and you get something greater than VZ, then you say that the diode is on and that it's going to drop exactly VZ volts. So if we take this equation and solve it for RL, you can find different values of where, like assuming that the RS is constant, or R I guess I called it here, and that the supply is constant, everything else is constant. If you change different levels of RL, it should turn off or turn on depending on the level of RL. So all you have to do is take this equation and solve it for RL. And that's what I've done here in the handout. So it's a VZ times R divided by VS minus VZ. So in our case, we have a 1.2K and a 30 volt supply and a 9.1 volt zener. Okay, so using that equation, it is a 9.1 volt zener multiplied by a 1.2K resistor, which is 1200, divided by a 30 volt supply minus a 9.1 volt zener. So it looks like for this one, it's about 522 ohms. So anything less than 522 ohms, we should see the zener diode turn off, and the output will no longer be held at that 9.1 volts. Anything greater than 502 ohms, we should see the zener diode be on, and the output will be held at 9.1 volts. Okay, so it looks like it comes out to about 522. So what this part of the lab is asking you to do is to try different values of RL and see at what point does the diode turn on or turn off. So initially you start with an open circuit. So that would be like RL equals infinity, right? So if you think about the voltage divider equation, with RL equal infinity, this equation right here, then obviously, if RL is infinity, it's like infinity divided by infinity plus R, right? So this fraction basically becomes 1 in that case. The fraction becomes 1, so it's just 1 times Vs. So that's definitely enough to keep the zener diode in the on state. So when it's open circuited, or when RL is open circuited, that's like the highest possible resistance you could have, and the zener diode will definitely be on in that situation. And then we're going to slowly decrease the resistance from an open circuit. So we're gonna use a potentiometer for this, or a variable resistor. So let me show you that in multisim. So go to place, component, and basic, and they have a component called the variable resistor. Typically, you would just use a potentiometer. Like if you're physically doing this in the lab, you would use something called a potentiometer, right? That's just a 3-terminal variable resistor, and you could just use 2 of the terminals as your variable resistor and leave the 3rd one disconnected. But they have a more convenient shape to use here. It just has 2 terminals. So since it's a simulation, we can use this just the same. It's just like a 2-terminal resistor that you can adjust essentially. So I'm going to connect one of these across the diode. I don't think I need to change anything else here except for maybe the values. So it's a 30 volt supply, and I think this 1.2K, I believe it was. And then the handout says to try different levels of resistance. So it says to use a 1K variable resistor, and then if you set that resistance to 100%, it'll give you 1K. If you set it to 80%, it'll give you 800, and then 600, 400, 100, and so on. So it's nice that it's 1K because it's easy to figure out the percentage, what level of resistance at different percentages. So we'll start off with 1K, and we have to set it to 100%. Okay, so currently I have a setup to measure voltage, and I have a setup to measure the total current, but I don't have anything to measure the individual currents. So if I want to measure the individual currents, I have to break the circuit either here or on the other side, for example. So why don't I clean this up a little bit and then make the ability to measure the currents for each as well. So let me get another meter. I think I'll just spread it out a little bit, drag this down. And I'm going to have this meter sit right here. And then I'll do the same for the load resistor. Oh. Okay, so this meter over here was just measuring the voltage. Okay, so hopefully you can see that just follow the different paths of current. So if you follow the current out of the supply, you see all of that current has to go through R1. And then when it gets to the node up here where the diode and the load resistor connect, then some of that current is going to go through the diode and some of that current is going to go through the load resistor. So notice how I have my meters connected. My meters are connected so that only the diode current goes through this meter XMM3, and only the load current goes through this meter. So I have to have it in series, like there should not be a connection between those 2 points there. Otherwise, the current would just bypass the meter. So you have to have a break in the circuit when you're measuring current, like we said before. So you notice the circuit is broken here, here, and there. And I'm providing a path for current to get back to wherever it was originally going before I put that meter into the circuit. So let me just make sure all these are set to current. Okay, and currently my meter is set, or my potentiometer, my variable resistor is set to 50% resistance. So I want to set that to 100. I want to start it out at 1K. Okay, so it seems to be working here. So we see the output voltage is about 9.07 volts, which is good for a 9.1 Zener 9.1 volt Zener diode. So like we said before, it is on, and I can just adjust this potentiometer or variable resistor to get different levels of resistance, and then watch how all these meters change. So this over here would be our source current, the 17. So we see there's 17 milliamps total from the source. 8 milliamps of that 17 goes to the Zener diode, and then 9 milliamps goes to the load resistance. And it should make perfect sense that that's why that much current goes to the load, because whenever the Zener diode is on, it's maintaining a constant voltage across that load. So if you have 9.069 volts across a 1K resistor, then you're expecting to get 9.069 milliamps for that. So as long as the voltage is held constant, the current through that resistor has to also be constant. So remember how we said that the Zener diode will take any extra current that comes about. So we can try different values of load resistor here by just adjusting the slider. So if that's at 1K right now, it's 100% of 1K, so that's 1,000. If I go down to 80%, that'd be 80% of 1K, so it should be 800 ohms now. Effectively, there's 800 ohms for my load. And you can see the values on the meters changed. The total source current didn't really change. It's still 17 something, 17.4. What did happen though is that the diode current used to be 8, I think it was. 8, I think this was 8 and this one was 9. So the diode current decreased by about 2 milliamps and the load current increased by about 2 milliamps. Of course, the load voltage didn't really change much. I think it was 9.059 or something before. So now it's 9.061. So the Zener diode is doing its job and maintaining a steady voltage across those 2 points. So we got very little change in voltage, but the current through the diode did change and the current through the resistor did change. And again, that makes sense because now we lowered the resistance. So now we have that same voltage, 9.06, but now it's 9.06 divided by 800 instead of 9.06 divided by 1K. So by reducing my load resistance, I should get more current flowing into the load at the same voltage. And that's exactly what I see happening here. So the load current increased, the Zener current decreased. And then you can go through and try some of the other points. So remember, we calculated this initially to be about, we said that the Zener diode would turn off at 522 ohms, if I remember correctly from our calculation. And using that formula from the handout, if you solve the voltage divider equation for RL and then plug in our particular values, you get 522 ohms. So we would expect the Zener diode to turn off around 522 ohms. Okay, so let's decrease down to 60%, see what happens. 60%, you see the voltage is still 9 something, right? So it's still, the Zener diode is still regulating or still on. And you can always verify that also by looking at the current through the Zener diode. Notice that we have 2.4 milliamps still. So the total supply current didn't really change, 17 milliamps again, 17.4 milliamps. The Zener diode current went down even further. It's down to 2 now. From initially it was at 8. And the load current increased even further. So notice that it still adds up to 17. The only thing that's changing as we're decreasing the resistance is that more current is going to the load and less current is going to the Zener diode. Right, so it is still on at 60%, and 60% of 1K would be 600 ohms. So we're expecting it to turn off at about 522 ohms. So let's try going something less than 522, which would be, anywhere like, let's say 40. 40% would be 400 ohms. So now my load is 400 ohms. That's too small for the Zener diode to be on, right? So if you calculate voltage divider with 400 ohms and 1.2K, you'll find that this voltage is not enough to exceed 9.1. And what do we see happening here? Well, we see that the supply current did change. It used to be, what was it, 17.4? So the supply current did change now. The diode current is basically 0. It's 12 picoamps. Pico is 10 to the minus 12. So this is, 0.0000000, but it basically 0 amps. So this diode is basically off now. And whenever the diode is off, it's not holding the voltage at any particular value. So we would not expect to see 9.1 over here. And indeed we don't. We see 7.5 volts on the output now. So the voltage divider is not providing enough voltage to the diode to allow it to be on. So it is currently in the off state, and it's basically acting like an open circuit, right? It's not changing, it's not doing anything at the moment. There's no current flowing through it, and it's not holding the voltage at any particular value. So now the voltage is purely determined by the voltage divider equation. So if you did 30 volts times 400 over 1.6, you should get that 7.5 volts. So 30 volts times 400, that's the value of the load currently, divided by 400 plus 1.2K, so that's 1200. So you see exactly 7.5 volts, theoretical. And that's what we're measuring on that meter. So that's doing exactly what you would expect. And any further decreases of our the load resistance is going to keep the diode in the off state, right? So now I made this load resistance even smaller, so that numerator in my voltage divider equation will get even smaller. The voltage will go down. It went down from 7.5 down to 4.286, and the current through the diode will still be 0, right? Because it's still off. It's still in the picoamp range, which is essentially 0. There's a small amount of leakage current, remember? But for all practical purposes, we could just say that that's an open circuit and 0 amps are flowing through it. And the supply current did increase a little bit again. So originally we had 17, and then I think we had 19, and now we have 21. The reason the total current is increasing, if you think about it, is imagine just removing this diode, and then you have 2 resistors in series left, right? If you have 2 resistors in series and you're decreasing the resistance of one of them, then that would make sense why the total supply current is going up, because you're decreasing the total resistance every time you do that. Okay, so that's how you can fill out that table in the lab handout. So you're going to do this, for measured and theoretical. So you can just run that voltage divider calculation each time, figure out what V out should be. So what should V out theoretical be for the open circuit? This should be 9.1, right? Because if you do that voltage divider equation, you're going to get infinity over infinity, which is just going to be 1 in this case. So you're going to get the voltage applied to the diode is definitely enough to turn it on. So this would be V out is like 9.1. And we already know, like, anything above 522, the V out should be 9.1. Anything below 522, which would be like these bottom 2 values here, V out will be whatever you get from the voltage divider calculation. So remember, it was like 7.5 and something else, 4.286, I think it was. So those are the values you should get for V out. What would be IZ theoretical here? Well, if the Zener diode is on, then it's going to have some amount of current. So for these 4 rows here, you're going to have some amount of current flowing through the Zener diode, right? Once you get down to 400 ohms, the Zener diode will be off. So you'd expect basically 0 current for these last 2. And then for the load will have some kind of current through all of these different situations, except for this one, because this one, the load is an open circuit. So when the load is an open circuit, there's going to be 0 current flowing through it. Any other value of RL will have some level of current flowing through it. Yeah, and then you can just calculate that like we just discussed. So calculate all these values theoretically, and then measure all those values in multisim, and then compare with what you got, and then calculate the exact level of resistance also. You don't necessarily need to do that ahead of time. I did that anyway, but you can make all these measurements without really knowing what you're supposed to get, and then figure out what you're supposed to get later. That works as well. So yeah, so compare your measured and theoretical data. Does your lab data show at what load resistance the Zener diode transitions from being off to on? We know the transition should happen somewhere between 600 and 400. it's supposed to happen exactly at 5:22, but we didn't use exactly 5:22. We did something above 5:22 and something below 5:22. Okay, so I think that's all there is in this lab handout to discuss. So I think we'll call it a day here. And sorry about the confusion again. I should have checked the calendar before I came. Next week, the next 2 weeks, I think it's like every 2 weeks we're in, every 3 weeks, I guess. So the next 2 weeks we are in person, and I think the third meeting after that is remote again. So I won't make that mistake again. I'll make sure to double check the calendar, and I'll also try to remind you the week before. So next week we are in person.